Welcome back to Innovashinka. Now that we've learned how to build and train a linear regression model, it's time to dive into an equally important step, model evaluation. Why is this crucial? Well, creating a model is only half the job. The real test is determining how well your model performs, particularly when it's exposed to new, unseen data. The primary purpose of evaluating a machine learning model is to understand its accuracy and reliability. We need to ensure that the model doesn't just perform well on the training data, but also generalizes effectively to real-world data or new datasets it hasn't encountered before. This process of evaluation helps us figure out if our model is overfitting, learning too much from training data, including noise and outliers, or underfitting, failing to capture essential patterns in the data. A well-evaluated model strikes the right balance, offering accurate predictions across different data scenarios. When evaluating linear regression models, we focus on certain key metrics like mean squared error, MSE, root mean squared error, RMSE, and R squared. Each of these metrics gives us a different perspective on the model's performance. MSE measures the average of the squared errors or differences between the predicted values and the actual values. Squaring the errors ensures that larger errors are given more weight, helping us focus on significant deviations. RMSE provides the error in the same units as the target variable, making it easier to interpret in real-world terms. If we're predicting house prices, for example, RMSE gives us an idea of how far off the model's predictions are in thousands of dollars. R squared explains the proportion of variance in the dependent variable that is predictable from the independent variables. It gives us an idea of how well our model explains the data, with values closer to 1 indicating a better fit. Evaluating the model helps us decide if it's good enough to be used in real-world applications, and it informs us on whether we need to fine-tune or improve the model. In this way, model evaluation serves as a critical feedback loop in the machine learning process. Let's explore some common metrics for evaluating linear regression models, focusing on how they relate to actual values and predicted values. Mean squared error, MSE, measures the average of the squared differences between actual values y and predicted values y hat. It is calculated by taking the differences between each actual value and its corresponding predicted value, squaring those differences, and then averaging them. By squaring the differences, MSE emphasizes larger errors, making it particularly useful for identifying significant prediction mistakes. Next, we have root mean squared error, RMSE, which is simply the square root of MSE. This metric provides the error in the same units as the dependent variable y, making it easier to interpret. RMSE gives a clear indication of the average magnitude of the prediction errors. Another important metric is mean absolute error, or MAE. Unlike MSE, MAE calculates the average of the absolute differences between actual and predicted values, treating all errors equally. This metric gives us a straightforward view of prediction accuracy without emphasizing larger errors. R squared, often denoted as R squared, is a key metric that tells us how well our model explains the variability of the dependent variable. A value close to 1 indicates that the model fits the data well, while a lower value suggests poor fit. R squared compares how well our model performs against a baseline model that uses no predictors. For models with multiple predictors, we use adjusted R squared. This metric corrects the R squared value based on the number of predictors, helping us avoid overfitting. It ensures that adding irrelevant variables does not artificially inflate our model's performance. Lastly, we consider residual standard error, or RSE, which measures the typical size of the residuals, essentially the differences between observed and predicted values. A lower RSE indicates a better model fit, as it means the errors are smaller on average. Together, these metrics provide a comprehensive evaluation of how well a linear regression model performs, helping us make informed decisions about model accuracy and suitability for our data. Now, let's dive deeper into the concepts of overfitting and underfitting. Overfitting is like memorizing answers for an exam instead of understanding the material. When a model is overfitted, it becomes highly specialized to the training data, including all its peculiarities and noise, which means it loses its ability to generalize to new, unseen data. Imagine training a model on a small dataset with numerous features. The model might find intricate patterns that don't hold true in the real world, resulting in high accuracy during training, but disappointing performance during validation or testing. On the other hand, underfitting occurs when a model is too simplistic to understand the underlying structure of the data. It's akin to studying a single chapter for an exam, but expecting to perform well on the entire syllabus. In this case, the model fails to capture essential relationships between features and outputs, resulting in poor accuracy on both training and test datasets. A classic example of underfitting is using a linear model to predict a nonlinear relationship. Balancing between overfitting and underfitting is crucial for developing effective models. Techniques like cross-validation, regularization, and choosing the right model complexity can help achieve this balance, ensuring that the model is both accurate and generalizes well to new data. Now that we've built a solid foundation by understanding linear regression theory and how it works, it's time to move towards something more practical. In this section, we're going to take all the knowledge we've accumulated so far and see how it applies to real-world problems. But before we dive into the code, let's first understand the concept of preparing our data and why it's such an essential step. Why preparing data is crucial. In any machine learning process, it's important not just to understand the algorithms, but also to ensure that the data we feed into these algorithms is structured properly. One of the key elements of this is splitting our dataset into two parts: training data and testing data. This is critical because we want our model not just to learn from existing data, but to also make accurate predictions on new, unseen data. To illustrate this, let's consider a problem where we want to predict house prices based on features like the size of the house. Let's go through this code line by line for clear understanding. Import NumPy as NP imports the NumPy library, which is essential for numerical computations in Python. It allows us to work with arrays and perform mathematical operations efficiently. Import matplotlib.pyplot as PLT imports the matplotlib library, specifically the pyplot module, which is used for plotting graphs and visualizing data. From sklearn.modelSelection, import train-test-split imports the train-test-split function from the scikit-learn library. It helps split the dataset into training and testing subsets, which is crucial for evaluating the performance of our model. From sklearn.linearModel, import Linear Regression, imports the Linear Regression class from scikit-learn. This class contains methods to create and train a linear regression model. Train-test-split function randomly splits the data into training and testing sets. Sizes and prices are the arrays we created earlier, serving as input, features, and out target respectively. Test size equals 0.2 specifies that 20% of the data should be reserved for testing, while 80% will be used for training the model. Random state equal 42. This parameter ensures reproducibility. It sets a seed for the random number generator, so you get the same split every time you run the code. Model equals linear regression creates an instance of the linear regression model. The model is now ready to be trained. Model.fit method trains the model using the training data. It learns the relationship between the house sizes, xtrain, and the prices, ytrain, by finding the best fit line. New size equals mp.array of two-dimensional array of 2200 creates a new NumPy array for the size of the house we want to predict the price for, 2200 square feet, formatted as a two-dimensional array. Predicted price equals model.predict new size. This method uses the trained model to predict the price based on the input size. It calculates the estimated price for a 2200 square foot house. plt.scatter function creates a scatter plot. The first call plots the training data, sizes versus prices, in blue, and the second plots the testing data in green. plt.plot function draws the regression line based on the trained model. It uses the training sizes, xtrain, to predict the corresponding prices, which are then plotted in red. plt.xlabel and plt.ylabel are the functions that is used to set the labels for the x-axis and y-axis respectively. plt.title sets the title of the plot, providing context for the visualization. plt.legend displays a legend on the plot, helping identify the training data, testing data, and regression line. And finally, .show displays the plot on the screen. Therefore, we can see the output below. In today's session, we explored the fundamentals of linear regression, building on the supervised learning concepts we've discussed previously. We started with an introduction to what linear regression is and how it's used to predict continuous values. We also covered the difference between simple linear regression and multiple linear regression, explaining how both types help us model relationships between input features and output targets. We then took a closer look at the linear equation, y equals mx plus b, and how it applies to solving real-world problems like predicting house prices. In addition, we discussed the importance of splitting data into training and testing sets to ensure our model performs well on unseen data. To cap it off, we framed a problem statement, setting the stage for coding and implementing linear regression, which we'll tackle in our next session. Don't forget to like, share, and subscribe to the channel if you found this session helpful. I'll see you soon in the next video, where we'll dive into hands-on coding for linear regression. Stay tuned.